Okay, the last question. This question is actually an O-level question, right? So this diagram represents a ball being dropped vertically. It rebounds and goes back to a highest point. Alright, so if I draw the motion, it will be something like that. It will be going down, it hits the floor, and then it bounces back up. But it doesn't go to the maximum, it only reaches a certain height. Alright, so why does it not reach the maximum? It's because some of the energy is lost during the rebound. So this will be the starting point A, this will be B, then when you rebound is C, then after that followed by D, where D is the highest point. Okay, so this is actually a speed time graph. That's why it is in this shape. So if you recall last time in the previous lesson, I actually draw this diagram using the velocity time graph. If we draw using a velocity time graph, it's going to go up. Okay, then suddenly there's a sudden change in velocity, then you go back up. These two are parallel to each other. So the reason why you see this kind of shape is because when you convert velocity time graph to speed, this region is reflected up. So when you reflect this region up, you get this shape. Alright, so it's nothing special, it's just a reflection on the x-axis of a velocity time graph. Alright, so let's look at the question. The first part, describe the motion of AB, very simple, uniform acceleration or constant positive acceleration. Second part, state how the graph shows the distance of AB is larger than CD. Again, very simple, you just say it's the area under the graph of AB is larger than CD. Nothing much to it. The more challenging question is C and D. Alright, C is the change in speed. Just remember, speed is a scalar. So I'm only interested in the magnitude because the scalar only has magnitude. So because of that, I just take final minus initial, which gives you 4. I don't care about the direction, alright? But if you look at velocity, which is the next question, it is a vector. Alright, so vector has magnitude and direction. So initially at point B, okay, the object is traveling at 12 meters per second. After C is traveling at 8. But these two are not traveling in the same direction. Alright, if you look physically at this diagram, at B it is going downwards at 12 meters per second. At C is just rebounded and is traveling outward at 8 meters per second. So although the values are different, the most important thing is that their direction are also different. So if you draw the diagram out, you're going to get something like that. At B, 12 meters per second, and then at C, minus 8 meters per second. You need to put a minus sign to show that these two are in opposite direction. So if you have a minus sign, you will straight away understand that if you want to find the change, it's the final minus initial, which gives you minus 20 meters per second. Alright, if you still don't understand why is this so, I can give you a very simple scenario. Imagine an object is traveling at 3 meters per second towards you. You hit it so that it goes backwards to where it comes from, and you hit it such that it has a speed of 3 meters per second. The question to you is, what is the change in velocity? You will tell me it's 6 meters per second. Why? Number one, you need to first stop the ball so it's 3 meters per second. After that, you need to give it another 3 meters per second to move backwards. So obviously the change is 6 meters per second. In the same way, if you want to go from 12 to minus 8, you must first remove the 12 meters per second downwards, then you must add the minus 8 upwards. So that's why the change is minus 20 meters per second. Alright. So that's all for exercise 2.4.